All right, so this video is a really fun one because it's basically just a bunch of puzzles, right? So the spectroscopy in general for organic chemistry is really fun, but it definitely takes some practice, and then you're going to have to look at a lot of different problems to really master the concept of mass spectrometry, for example. And what is this? It's a technique used for measuring the molecular weight, so MW molecular weight, and determining the molecular formula of an unknown organic substance. Now, in general, usually this mass spectrometry is used in conjunction with the nuclear magnetic resonance, so NMR, as well as IR, infrared spectroscopy. And so those are some videos that we'll do later, but for now, let's take a look at mass spec and how we do it. Here is an example of a mass spectrometer. Spectrometer, it's basically just the instrument that we use to obtain a mass spectrum. Okay, and so basically you insert your sample over here, and then it shoots through. That red dotted line is basically neutral molecules shooting through the instrument, and then they go through a series of plates. So we have a repeller plate, we have a negatively charged accelerating and focusing plate. Basically, we don't need to worry too much about the function of these things, other than the fact that what happens is it creates a molecular ion, and typically, although there is a negative mode as well as a positive mode, the types of problems that we'll be going over in this class are only for positive mode, meaning the molecular ions that are formed in the mass spectrometer are cations. And so since we have a positive charge, they are basically affected by a magnet and its magnetic field. And so that's what happens here. Depending on the strength of the magnet, you can, as well as the mass to charge ratio, these ions can be deflected. And so that's basically what's happening here. They're changing their path and making a hard right turn, right? And so only a few ions or a specific mass will actually make it through the ion slit and then make it to the collector, and that's based off, again, the strength of the magnet as well as the mass to charge ratio, which is m over z, so the mass of the ion versus the charge of the ion. And typically the charge of the ion in these particular problems that we'll see are always positive 1. So z is usually positive 1. Okay, and so this is actually really convenient because when we have a positive 1 charge, then that means we only lost 1 electron, right? So lost 1 electron. And so looking at what this technique allows us to do, it basically measures the molecular weight. And this is because at the collector, we are examining the mass of this specific compound, and it's also based off of the strength of that magnetic field. And since we only lost 1 electron, then that means whatever shines through the detector is pretty much the molecular weight of our actual organic substance. And so what I mean by that is, if we have M is in the molecule or the sample, and then we have a beam of electrons shining through. That's basically what's happening in this area right here. What happens is it ionizes it, so it makes a radical cation, and so it's a positive with an unpaired electron because 1 electron was essentially ejected off of that molecule. And this right here is called a radical cation because it has one unpaired electron, making it a radical, and it also has a positive charge, which makes it a cation. And again, what I was trying to say is the mass of these two things is the same. So the mass is the same. And so that's why this particular technique is really useful, because we've ionized this thing and now we've gained the mass of it, and now we know the mass of our organic substance. Okay, and this is the, oops, sorry, let me change that color. So this is the charged particle that flies in the magnetic field. So charged particle that flies through the magnetic field. Another thing to mention is the radical cation is also called the molecular ion or the parent ion. And so this guy right here is the parent ion. Okay, and so we call this the parent ion, obviously, because this is the name, or this is the molar mass or the molecular weight of the organic substance. So the parent substance that you put in the mass spectrometer originally. The reason why this is important is because of what happens to these molecular ions as they fly through this the analyzer tube. But first, let me show you here. So as it goes through the collector, we end up getting to ultimately convert that data into a mass spectrum, right? And so what does that look like? Well, here's an example for you. And there you go. So here is basically a bunch of peaks that are showing up. They're basically just, they look kind of like histograms almost. But as you can see on the left side, this is the relative abundance of these particular ions. So remember, anything that goes through and is actually observed on the mass spectrum has to be a cation. Okay, so anything observed, I'll say must be charged, meaning it has to have a positive charge in this case. Okay, and so what we have here is a mass spectrum of methane. So CH4, as you can see, because of the label here, the molecular ion at M over Z, so the mass to charge ratio, is 16. So that is the M peak, so the molecular ion peak or the parent peak. Okay, and the reason why this is the parent peak is because if we look at the data that was given to us, we would see that this is the molar mass, or 16 is the molar mass of methane. So we have carbon equals 12, and then a hydrogen equals 1 times 4 of them gives us 16 atomic mass units, and that's essentially what we have detected with our mass spectrometer. Now, the M+1 peak, notice how it's really, 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 really small. You gotta like really zoom in there, and it's pretty much nothing. The reason why that's there and it's so small is because we do have a very, 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 very small amount of carbon isotope that is actually not carbon-12 but carbon-13. So it's 1 atomic mass unit heavier, and so that's why we end up getting that M+1 peak. Okay, so the M+1 peak in this case, +1 peak is equal to, or is contributed, it's due to the presence of a carbon-13 isotope, due to carbon-13. Okay, And so this is, of course, something important to note and make sure that you're aware of. As you can see, there's a very, very small amount of that relative abundance of basically the mass to charge of 17. And then as you move down, further down, we have 15, 14, 13, 12, getting smaller and smaller and smaller in abundance. And this is pretty typical as you move down from the parent ion. Okay. The reason why is because the methane molecule undergoes something that's called fragmentation. So fragmentation. Okay, and this is basically when the molecule or bonds break to form fragments, right? So I sound like a Webster dictionary using the word in the definition, but we already know what a fragment is. It's just a piece of the molecule, right? Or it's just a piece of something, and so in this case, it's a piece of the molecule methane. So bonds break to form fragments, or pieces. I'll put pieces of original molecule. Okay, and let me go ahead and give you an example of what I mean. So, well, we can see that we have a mass to charge of 16, so that m over z. Let me do like this. M over z. When it's 16, is equal to a CH4 molecule that is a radical cation. Okay, so it's basically methane went through and we ejected an electron, but the methane, or I'm sorry, the mass to charge ratio of 15, that's when we lose one atomic mass unit. And the only thing on methane that weighs that much is a proton, essentially, and so, or a hydrogen atom. And so what we've done is we've lost an entire hydrogen atom, and so we end up with CH3 plus, and so that means we lost H dot, so a hydrogen atom. Okay, and that's why we don't have this radical anymore on the mass to charge of 15, but that's okay because we still have a positive charge on that molecule. Then we have a mass to charge of 14. Let's say we lost another hydrogen atom. That means we would get an H2 plus with another radical. Mass to charge of 13. Let's see if you can guess the right thing. Boom, we get that. And then 12, of course, is when we lose an additional proton or a hydrogen atom, and we get C plus dot. Okay, and so again, this is basically an explanation of the fragmentation process, and this occurs because we're essentially bombarding this molecule methane with high energy electrons, and so to eject an electron, and sometimes we just eject, in this case, a hydrogen atom. But if it were a more complicated molecule, it could fragment into bigger pieces. So like entire methane portions could fall off, or ethyl groups, or sorry, a methyl group, not methane, but a methyl or an ethyl or a propyl or isopropyl, and things like that can just fly off. And so that's the idea of fragmentation. So as you can see above on the top, the tallest peak in this particular mass spectrum represents that of methane, but and so this is the parent ion. However, the tallest peak in general in the mass spectrum represents something called the base peak, and this is actually just the most stable radical cation, which is helpful to deduce the structure of the organic molecule. And so, depending on how good your mass spec is, you can actually use this to distinguish between basically organic molecules that are extremely close in their molecular weight. One example would be like something, these aren't actually super close, but pentene versus, here, let me change that for you. Pentene versus pentyne. And I guess technically I should put a 1 in front of that. But what I mean is 1, 2, 3, 4, 5. This guy versus 1, 2, 2, 3, 4. Whoops, 3, 4, 5. And so the molar mass of this guy is 68, and or the molecular weight of each of these is 68 and 70, and the functional groups are very similar, and they have similar reactivity, and so it could be really easy just to go from or just to analyze our mass spec, analyze our organic molecules using mass spec rather than doing an extreme amount of organic chemistry to kind of differentiate between the two molecules, because they do have a mass difference of 2, and so this mass spec literally takes just minutes. You prepare your sample very quickly, and then you inject it into the instrument, provided it's well maintained, no problems, and you get your mass spectrum, and then you pretty much figured out what it is. It's really cool. In addition to that, it also allows us to kind of differentiate between organic, or identify certain functional groups. So for example, the presence of a nitrogen. Okay, so nitrogen, we'll put this, it does allow us to kind of identify the presence of nitrogen, chlorine, and bromine very, very easily. We'll get into a few other functional groups, but these 3 are kind of pretty straightforward. And so let's do the nitrogen first. One thing that basically the telltale sign of the presence of a nitrogen is that the organic molecule has an odd mass. Okay, and this is the key right here, the odd mass. That's like, okay, that's definitely a nitrogen then. And why would that be? Well, if you think about it, carbon has a mass of 12, and oxygen has a mass of 16, so those are both even, and they both have an even number of bonds. So carbon with 4, oxygen with 2, and then we can keep going. Basically, it turns out that everything they form is an even mass, and so if you do have an odd mass, then it has to have a nitrogen in it. And the reason why is because nitrogen is trivalent. Okay, so N is trivalent, and that means that it has 3 bonds. Okay, so for example, nitrogen having a mass of 14 binds to 3 hydrogens, each having a mass of 1, and so that means that the mass of this is 17. There you go. The presence of an odd, or the mass is odd, and therefore we had that nitrogen. So if you think about it though, what if we had 2? So let's do hydrazine. Okay, so this is 14, 14, 1, 1, 1, and 1. So this is 28, 29, 30, 31, 32. So basically if it has an odd mass, it has at least one nitrogen, okay? So odd mass equals at least one nitrogen. Okay, so that means it could have more, right? If it has two, we just saw that mass is going to be even. So unfortunately, this wouldn't be really helpful to identify if it has two nitrogens. However, if it has three, it would be odd again. So it has to have an odd number of nitrogens. So it could be 1, 3, 5, 7, 9, etc. And that would give you an odd mass. And then therefore you'd be able to tell that there's at least one nitrogen in there. Okay, so for example, let's try another one, but let's actually take a look at some mass specs. What I want to do first is kind of draw out some structures. Here is, curious if anybody knows this. Hopefully I don't get the structure wrong. And then we also have this one. Nitrogen. And then we got another thing there. Methyl. And this is where I ask, does anybody know what structure these are? And then somebody raises their hand and they say, I remember seeing that in another video you did. And that was dopamine. Here we go. And then, oh, I remember this one as well. This was caffeine. Because you said it looks like adenosine, kind of. And then, yeah. So, anyway, yeah. And notice they also have nitrogens. So 1, 2, 3, 4 for that guy. He's fancy. Let's take a look at some mass specs now. All right, so here are two mass spectra, and I kind of want you to kind of decide on which one is which, not even looking at the actual molar mass of the two substances. Don't calculate that, but let's just take a look at the features of the dopamine and caffeine. So dopamine has 1 nitrogen and caffeine has 4. So let's just zoom in on this first first mass spec, and that's the 150 mark. Then we got 51, 52, 53. So this is actually 153 for there. And then we've got, since this is 180 and this is 200, this is 190, and each of these is 2. So that's 192. And then there's 194, which is where this is. So the parent peak is 194. This one's even, and this one is odd. So the top one must be dopamine, right? Because it has an odd number of nitrogens and it has an odd mass. And this one, it must be caffeine. And they are, in fact, those substances. And so since we're on the subject, I kind of want to introduce something to you. It's actually a spectral database, and I don't know, let's see if we can just access it real quick. SDBS. For me, it actually pops up automatically, but it is the Spectral Database for Organic Compounds, also known as SDBS. So what you do is you want to click on that. Super awesome thing. Extremely useful. Oh, here we go. Now it pops up. And you always have to agree to this disclaimer that I never read, and I totally do, and I agree to it. And then you can insert a compound name. So let's just do caffeine. There we go. So what is this? Well, first of all, we got the molecular formula, sick. The molecular weight, 194. Hey, check that out. The MS stands for mass spec. C NMR is a carbon NMR. CH NMR is the proton NMR, which we will eventually get to. And then we have IR, which is the infrared spectroscopy, which we will also get to. And the Ys mean that they have spectra for those modes of analysis. And so we already saw the mass spec, but let's go ahead and click that. And there you go. It actually gives you a bunch of information as well. So it's really fun to kind of look at these. I would actually suggest maybe you use this as a source for practice once you do the homework problems. But then you can also see over here we have different types of analyses as well. So I'm going to go ahead and click this proton NMR one, and you'll see that pop up. And boom, this one actually shows the structure. It's got things labeled. And then this is just a sneak peek at NMR. So something to look forward to. Super fun. All right, so let's try, or let's move on to the another example of basically how useful the mass spec can be in kind of identifying just functional groups. It's not only giving you the molar mass of something, but like it's actually helping you determine if there's a nitrogen in there, or in this case, a bromine or a chlorine. Okay, so we have, so this is bromobenzene. It's a benzene ring with the bromine on it. Fancy naming, right? So this is, you guessed it, chlorobenzene. Okay, so I got some mass specs underneath here. So basically, let's take a look at this. And well, no, I'm sorry, I have to tell you what the rule is, right? And so these ones are actually really useful because just like carbon has a very small isotopic abundance of carbon-13, bromine and chlorine have different isotopic abundances for their bromine. What is it again? 79, and bromine 81, and then chlorine 35 and chlorine 37 also have a pretty large, there's definitely a substantial amount of each of these isotopes. And for bromine 79 and bromine 81, it's approximately a 50-50 mixture. Okay. And so that means that we will have something called an M+2 peak. That are basically going to be equal in height. Sorry, that would be more appropriate to put. So that M+2 peak means that we will have a peak that is approximately 2 units higher, and it will be equal in height to that that other peak. So that M+ peak, equal in height to M+ peak, if we're saying that there is an M+2 peak. So for chlorine, it's a little bit different. It's actually going to be a 3-to-1 ratio, where we have 3-to-1 ratio for more chlorine 35 than chlorine 37. And so that means that our M+2 peak is going to look and appear in that ratio as well. So we're going to have an M+2 peak of at a 3-to-1 ratio. Okay, so it's basically just going to look they're going to be 2 units apart from one another, and they're going to have a significant size, such like they're going to be obvious in appearance, but then they're also going to be in that specific ratio. So the reason why I'm bringing up these mass spectra is so that you can actually visualize what I mean by this. And so basically, bromine is a 1-to-1 ratio, chlorine is a 3-to-1 ratio. So let's take a look at what we mean by that. Okay, so as you can see, these peaks right here are approximately 1-to-1 in height, and then these ones right here are about 3-to-1 in height. And so the way, I would just kind of slice it right here, and then imagine another one here, and then this. So this would be 1, 2, 3, and so that's obviously a 3-to-1 ratio. 3-to-1 ratio means that this one would be chlorobenzene. Okay, and so this being a 1-to-1 ratio means that this compound would contain a bromine, and in this case is the bromobenzene. So the reason why this is useful is because we can immediately determine that there is a bromine present just by these M+2 peaks being approximately equal in height, and then these M+2 peaks being approximately 3-to-1 ratio. So let's zoom in just to make sure that we're good on that. This is 50, 55, so this is 56, and then this is 58. So this is a 156 and then a 158, and so that's what we mean by there's an M plus and then there's an M plus 2. Okay, and let's take a look at this one. This is 110, 11, 12, so this is 112, and then a 114, and then again this is an M plus peak, and then we have an M plus 2 peak, usually it's called, and then that's just the additional 2 units of mass. So these are really useful because sometimes you can just get a really large molecular mass, and then you more or less are going to have to assume that it's all carbons and hydrogens until you can prove otherwise. And so now we figured out how to kind of determine that there's a nitrogen, a bromine, or a chlorine present in our actual organic molecule. Now what I wanted to do is introduce the rule of 13 and kind of go over a problem using the mass to charge ratio to propose some structures. All right, so for example, let's just start off with the basics. So propose a possible molecular formula. For a compound with a molecular ion at m/z equals 154. Okay, so your book does it a little bit differently than I do. So, for example, I kind of give you the rule of 13, and the rule of 13 says that you should divide this 154 by 13, and that gives you 11.85 for that value. And essentially what I'm saying is that initially what we're going to have is 11 carbons and then 11 hydrogens, and that obviously does not add up to, so we're using this number right here as the whole number because we can't have 0.85 units of carbon and hydrogen. Okay, so maybe you may or may not have noticed, but that 13 represents CHs. Okay, so if I have 13 units of them and I divide that into 154, I get 11.85. That means I can use 11 CH units to be very definitive about that. And so since we used C11 H11, there's that portion 0.85 that's left over, right? And so 11 times 13 is equal to 143. Okay, so this mass is equal to 143, and that's obviously not the whole 154, so we need to subtract the 2, and what we get is 11 again. And so what that means that is what we want to do is add 11 to the total number of hydrogens. Okay, so now what we get is 11 H22. Okay, and so this actual mass is it's just a general proposal. It's one of very many proposals actually. So think about it. C11H22. You might be thinking, wait a minute, Jess, right? I thought hydrocarbons had to have the formula CnHn plus 2. If that was C11, then the hydrogen count would have to be H20. What? I'm sorry, 2n plus 2. That would have to be 24. Yeah, you would be correct for remember this is a saturated hydrocarbon, so that's a straight chain hydrocarbon with nothing fancy going on, and it has all the hydrogens that it can possibly have. But we can have ring structures. Remember cycloalkanes can have the formula CnH2n, and that would actually work out perfectly for us because that would be C11H22, which is exactly what we proposed. Okay, so this leads me into a discussion on other possibilities of having heteroatoms and how they might affect the total hydrogen count. Okay, so this is something called degrees of unsaturation. So degrees of unsaturation. Okay, so what do I mean by that? Well, if a saturated hydrocarbon means that they can have all of the hydrogens, it has all the hydrogens it could possibly have, meaning it follows this formula, then unsaturation means it's missing some hydrogens. Okay, and so this can obviously be, we just saw an example of a ring, okay, or it could be just an alkene, right? So an alkene is an unsaturated hydrocarbon, and so it's missing some hydrogens. Okay, and then we also have an alkyne, but we can also affect the presence of, or the number of hydrogens by the presence of nitrogen or X atoms. So where X is equal to fluorine, chlorine, bromine, or iodine. Now think about it this way. So let's say we had propane, okay? And now propane has 3 carbons, and therefore it should have 2n plus 2 hydrogens, which is 8 hydrogens. And we can see that 1, 2, 3, 4, 5, 6, 7, 8, right? All is good in the world. Well, let's say we had a propane molecule, or at least the skeletal structure, but with a nitrogen on it, and it wasn't affected, or it wasn't charged or anything. That means that nitrogen has to have 2 hydrogens on it because nitrogen is trivalent. Okay, So that means it would have C3. We can almost ignore I'll put the nitrogen at the end because we don't really care about the presence of the nitrogen. We're just focusing on hydrogens. What's the number of hydrogens that we have? Well, the way I like to think of it is we have 1, 2, 3, 4, 5. So these weren't affected, right? But the blue, there's 2 here. This nitrogen took the place of, let's say, that hydrogen, right? But it replaced it with this one, okay? But then since nitrogen is trivalent, it actually had to have an additional hydrogen on it, and so that's where nitrogen kind of screws up the degrees of unsaturation calculation. And so what we end up having is not 8, but 9. So we've got 3 here, 4, 5, 6, 7, 8, 9. And so with a nitrogen, we get, we add a hydrogen, or we get an additional hydrogen. Okay. Now, let's take a look at the presence of, since we're in red already, when we have an X atom. So let's just actually use a chlorine instead of just using an X. Okay, well, how does this affect the number of hydrogens? We got 1, 2, 3, 4, 5, 6, 7. So this chlorine actually took the place of that hydrogen, but it really didn't affect it. It doesn't have any double bonds or anything, so it actually just took the place of it. And so the formula is C3H7Cl. Okay, so when we have so with an X atom, we lose an H. Okay, but technically, when we have a nitrogen or an X atom, these compounds are not unsaturated. Okay, so these are not unsaturated. However, they can be deceiving and almost make us believe that they are unsaturated, just because if we weren't careful, we would count like, okay, well, this doesn't have the proper number of hydrogens, and so if it doesn't have all the hydrogens it could possibly have, then it must be unsaturated, right? No. So remember, unsaturation means that we pretty much have a ring, an alkene, or an alkyne, okay? So we need these to be unsaturated. Okay, SAT'(D) is an abbreviation for saturated. Okay, so these compounds containing nitrogen or X atoms are, again, they are not unsaturated. They just threw off the count because of their trivalency, or they're taking the place of a hydrogen. Okay, so what does this mean? That means that when we are calculating the degrees of unsaturation and we do have the presence of a nitrogen or a chlorine or fluorine, bromine, iodine, we need to account for these when we are calculating how many hydrogens this molecule should have. Okay, so if we are degrees of, so DUs, degrees of unsaturation, are equal to 2C plus 2 plus N minus X minus H divided by 2. Okay, so for example, if I wanted to calculate the degrees of unsaturation of cyclohexane, what I would do is I would first of all calculate the number of, or we need the molecular formula, I'm sorry, C6H12. Okay, so this is cyclohexane. Okay, let's say we wanted to calculate DUs. Well, what we do first is take a look at the number of carbons and calculate how much we should have. It's almost like a theoretical, okay? How much does a saturated compound have? So C6H14. Remember, this is a CnH2n plus 2. That's a fully saturated hydrocarbon. Okay, so now that we see that we have a difference between the 14 and 12, what we do is we determine, we actually just have to subtract the 2. So 14 minus 12 divided by 2 is equal to 1. So that means we have 1 degree of unsaturation, which is due to the presence of that ring. So one ring, if you're just looking at a substance, then one ring is a degree of unsaturation. If you have 2 rings in that molecule, then you automatically have 2 degrees of unsaturation. Okay, and each pi bond, so this pi bond right here is a degree of unsaturation, and then these are also going to be degrees of unsaturation. So this alkene is 1 and alkyne is 2 and a ring is 1. Okay, so if you're visually looking at it, you can just add them up, but if you need to calculate it, what does the DU represent? It represents either a ring or pi bonds. Okay, so the reason why I just jumped straight to 14 is because remember that this 2n plus 2 is a 2c plus 2, and that's what this unit is right here. So you can just actually put the number of hydrogens in saturated compound if you want, and then you go from there. And so since we didn't have a nitrogen or an X compound, or a halogen, then we didn't really need to plug those in. But let's say we did. Let's say we had a problem where we were asked to calculate the number of degrees of unsaturation. So calculate DUs. Okay, so I'm gonna make this up. C8, let's see, 4, 5, 6. Let's say this was our formula. Okay, now basically when you're calculating degrees of unsaturation, what you want to do is determine what a saturated hydrocarbon would have if it had the same number of carbons. So in this case we have 8. So what we want to do is C8H18. That's what the normal saturated hydrocarbon would have. So this would be a saturated compound. And essentially what we have is obviously a very large difference between the number of hydrogens, but we also have the presence of that nitrogen and chlorine. So what we want to do is look at our formula. Remember that 2C plus 2, it represents the number of hydrogens that are in the saturated compound. So the number of DUs is equal to 18, because we calculated that already, plus the number of nitrogens minus X minus H divided by 2, plus the number of nitrogens, which is 1, minus the number of chlorines, which is 1, minus the number of hydrogens, which is 10, divided by 2. And that should give us our degrees of unsaturation. So this obviously cancels out, so it's 18 minus 10, which is 8 divided by 2, which gives us 4. Okay, so this particular substance, based off of its molecular formula, has 4 degrees of unsaturation. And remember, this can come in the form of 1 ring, or it could be 4 rings, or it could have let's say a 5-membered ring. That's 1 degree of unsaturation with 2 double bonds in there. That's 2 more. So total, this thing right here has 3 degrees of unsaturation, and so all we would need is some sort of pi bond or another ring in that structure. Okay, well, it turns out, remember, I'm telling you now, if you got a lot of degrees of unsaturation, which is maybe if you have 4, the first thing you want to think of when you're trying to propose a structure, at least, is a benzene ring. Because this has 1, there's a pi bond, that's 2, there's another pi bond, that's 3, and there's another pi bond, that's 4. And so the fake molecule that I just made up for this particular problem was this right here, and this has 4 degrees of unsaturation, which we actually determined from the molecular formula. And again, we just plugged that into this formula right here. Okay, and so that's pretty much all we really need to calculate the degrees of unsaturation. The reason why I wanted to bring that up is because we can actually bring this a little bit further. This problem up here where we had C11H22, because then we can start throwing in nitrogens or chlorines, but that does ultimately affect the number of hydrogens that we would have, and that's why it's important to understand the degrees of unsaturation, because we also want to know what's possible and what's not possible. So, for example, if we went from C11 and let's say we removed one of those carbons and we went to C10, well, that's a mass of 12. That's 12 units basically. And so what we have to do is something with that 12, and we could just technically add it to the total number of hydrogens, right? But 12 plus 22 is 34 hydrogens. And we already know that a saturated hydrocarbon, meaning the maximum number of hydrogens that this 10 carbon containing compound could contain, wow, that was a lot of C words, it can only have up to 22. Okay, so C10H22 is the saturated compound based off of that formula. And so we know we cannot do that. So for a compound only containing carbons and hydrogens, this is actually the only option that we can have. But let me go back down. Let me go down here where we have space. If we did have C11H22, what we could do is start swapping out nitrogens and oxygens. So for example, if we wanted to swap out an oxygen, what we could do, swap out some carbons and hydrogens for oxygen. What we usually do, the best route to do this is subtract 1 carbon and then subtract 4 hydrogens, okay? So that means we go to C10H18 and then we just add an oxygen. The reason why we do this is because one of these guys is 12 and 4 of these guys is 4, which equals 16, which is exactly what an oxygen's mass is. And so that's pretty much what you want to do in order to swap out 4 other heteroatoms. So if we wanted to swap out 4 from C11 to H22 with a nitrogen containing compound, what we can do is it could be a variety of things, but we could remove 1 carbon and 2 hydrogens, right? And so that would give us C10H20 with a nitrogen compound, okay? And again, if we want to propose the validity or suggest that this is a valid structure, we want to make sure that this is in the realm of possibilities based off of degrees of unsaturation, and or in this case, saturation. What does a saturated compound contain? How many hydrogens with one nitrogen in it? What would it be? And then that's when we would go up to this formula and start plugging things in, because we really want to have 0 degrees of unsaturation if we're gonna go from this C11H22 to that C10H20N, and that's because this was the, that had 1 degree of unsaturation. So I'm sorry, I misspoke, but long story short, this is basically how we calculate degrees of unsaturation, and then this is how we can start exchanging out for heteroatoms to determine other possible molecular formulas. All right, so I think it's time we talk about practice. What am I talking about right now, right? So let's see if we can figure this problem out. Basically, determine a possible molecular formula from this mass spectrum. Molecular formula. Okay, now we're looking at this. We're looking at it very closely. What do you want to do first? Well, for me personally, I like to look way over here. I see 2 itty-bitty peaks. Looks like one of them is right here at 122. That other one is right at about 124. All right, so what we need to remember is that this is an M plus peak, and this is an M plus 2, right? And so what do we need to look at next? Well, these are actually approximately 1-to-1 ratio for the 122 and 124. And so that tells us that we have a bromine in there. Super cool. And so what we need to do now is figure out an approximate molecular formula. Well, we know we have a bromine in there, right? But how many carbons and hydrogens do we have? Well, since it's bromine and the isotopic abundances of bromine are 79 and 81 at 50-50, that means the average of the mass in general is about 80. And so it also means that the molar mass of this particular substance is actually 123, because we're going to get an average of those two masses. And since we have an average of 123, what we want to do is, remember, the rule of 13. Rule of 13, divide that baby by 13. Oh, I'm sorry, JK. Since we already know that we have a bromine in it, what we actually do first is subtract 80 from there. So 123 minus 80 equals 43. Okay, so that means we already have a bromine in our molecular formula, so I'll leave that there. Now we can divide this by 13. So 43 divided by 13 is equal to 3.3. So this is equal to 3.3. And obviously, remember what this means is we have C3H3, and then we have a remainder of 0.3, right? And so basically what we need to do is convert that to whole numbers for hydrogen. And so the mass of this particular almost like a skeleton or a suggested initial value is 12 times 3, 36 plus 3, which is 39. So the mass of this is equal to 39. And since we had 43 to work with, 43 minus 39 is equal to 4. Okay, so that means we need to add 4 to there. Okay, so that leaves us with C3H7 and then Br. Move that over. Oh, sorry about that. Move that over. So, oh my goodness. So the proposed molecular formula is C3H7Br, and so you can also double check your work to make sure that that actually works out. But long story short, what that should be is there's 3 carbons. There's a hydrogen, a hydrogen, 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 hydrogen. So this is a possible structure, right? We've got 3, 4, 5, 6, 7 hydrogens, 1 bromine, and 3 carbons. That's not the only one, though. We can actually have this as well. So these are definitely the 2 structures that are possible for the given molecular formula and the mass spectrum. While we're on the topic of bromine, let's propose another molecular formula and then see if we can propose a structure. So let's say we had the molecular formula of C3H5Br, and I want 4 structures, 4 possible structures. So what we want to do first is take a look at the degrees of unsaturation, and that way we know how many rings or double bonds there are, and we can easily move forward from there and propose all the possible structures, right? And so remember, the saturated compound has we still take the number of carbons. We have C3, but it's 2n plus 2 for the hydrogens, so it's 8 hydrogens. And obviously there's a difference here, right? So now what we want to do is calculate the degrees of unsaturation. The du equals, since we have a bromine present, that actually takes the place of a hydrogen without contributing to degrees of unsaturation. And so what we want to do is use this number 8 minus the number of bromines, or X atoms, which is 1, minus the number of hydrogens in the compound in question. And so that's 5. Divide all of that by 2, and that gives us 8 minus 6 divided by 2, which is equal to 8 minus 6 divided by 2, which is 1 degree of unsaturation. All right, so which means that we either have 1 pi bond or 1 ring. And so how can we arrange 3 carbon atoms, 5 hydrogens, and 1 bromine with this criteria and to give us 4 different structures? Well, what I would do first is just draw a straight chain and create a pi bond. Okay, so we could put that pi bond on either side, it doesn't matter. But now we want to put a bromine somewhere, and that should take care of one of our structures. Now we have pi bond in that same spot, and we can move that bromine to this middle carbon. We can also do another structure where we have that bromine directly bound on that terminal carbon with the pi bond. So that pretty much takes care of all the straight chain alkanes, or the alkenes, and therefore it takes care of our 1 pi bond. We can actually draw a structure with a ring as well, and there's only going to be one of those, however. So if we do a ring structure with the bromine, it doesn't matter if the bromine is here, here, or here. It would always be the same structure, and we can't draw another ring structure with the bromine. And so these would be our 4 options. And you technically could have some cis-trans isomers, but all I was asking for was 4 structures. So great job, you got 4 structures. And that's pretty much it. Have fun with the material and get some practice in for sure.